Good morning, children. Today this is your 12th physics, chapter 4. This is the children's second last topic of the chapter, that is magnetic effects of current. So today we are going to study about moving coil galvanometer. Right, children? So moving coil galvanometer, children, it is a device that is used to detect and measure the small electric current. This moving coil galvanometer, it works on deflection method. Deflection method means when we place this device in any electric circuit, then we know that the current will flow, the current that is flowing in the circuit. Due to the current that is flowing in the circuit, there will be deflection in the coil, this red coil, which is present in the galvanometer. And this deflection is the indication of how much this coil will get deflected. That is the indication of the amount of current that is flowing in the circuit. Right? So it is based on the, let's talk about the principle. It is based on the principle of the deflection, right? So because of the torque, the deflection occurs in the coil. Because of the torque, the deflection occurs in the coil, which indicates the measure of current or voltage in the circuit. The torque is how much torque will be produced, that is given by the formula NIAB sin theta, where N is the number of turns in the coil, I is the current that is flowing in the your apparatus, right? A is the cross-sectional area and B is the external magnetic field B, right? And your theta, children, it is the angle between the area vector A and the magnetic field that is B, right, children? Now let's try to understand about the construction. So here, children, you can see that it consists of the concave shaped, this is concave shaped magnets, right? So these magnets, they produce radial magnetic field. That is the magnetic, here you can see that this is something circular region in between. So magnetic field is produced along the radius of this circle. That is your radial magnetic field, right, children? And here you can see that you are having your red color coil. Now this coil, it consists of large number of turns. So you have taken a copper wire, and on the copper wire you have wounded it, you have wounded the copper wire over some material. And the material which here you are using, means the winding of the copper wire, you have done on soft iron core. Right, the soft iron core, it is a ferromagnetic material, means the soft iron core on which this copper wire, has been wound, that will get magnetized when it is placed in external magnetic field, right? So the magnetic field that is produced in the coil will be more strong, and if the magnetic field B is more, then the torque which will be acting on the coil will also be more. That is what we want. We want the maximum torque to be acting on the coil, right? Now let's talk about the upper part of the coil. The upper part of the coil, as you can see, it is attached to two rings. First, it is attached to a spring, and second, it is attached to a pointer. Now, this pointer, as you can see, it can slide over the scale. Here you can see some readings have been shown. So, on this scale, the pointer can slide and it will give the measure of the current. Now, children, you might be wondering that why we are using here the radial magnetic field. So, children, there are two benefits of using radial magnetic field. Firstly is that whenever we place our moving coil galvanometer in any circuit, then we want that the maximum torque should be acting on the coil. If maximum coil will act, then that maximum torque will turn the coil, and then the pointer will be able to deflect easily. So if we want torque to be maximum, then children, B should be maximum, the magnetic field should be maximum. And what happens in radial magnetic field, that the intensity of the magnetic field at the center of the coil will be large, it will be maximum. Intensity of radial magnetic field at the center of the coil will be maximum, right? Let me show you one more diagram for this. If you see in this diagram, children, here the magnetic field is along the radius, right? So the intensity of the magnetic field at the center of the coil is maximum. That is what we want. We want the magnetic field to be maximum, and if magnetic field is maximum, then the torque will be maximum, right? Secondly, children, if we want torque to be maximum, then if we want torque to be maximum, then the angle, that is theta, between the magnetic field B and the area vector should be, the sine of that should be maximum. So sine 90 is maximum. So what happens in radial magnetic field? This is, suppose children, the upper view of the coil. So the area vector is coming outwards, that is, it is coming towards you, right? And the magnetic field, as you can see, the magnetic field is along x-axis and this is coming outwards. So the angle between them is 90°, right, children? Yes. So the theta is 90 and sine theta is 1. So radial magnetic field, it provides us two benefits. First thing, the intensity of radial magnetic field at the center of the coil will be maximum, which will make the magnetic field, maximum magnetic field available to the coil. So torque will be maximum because B is maximum. Second, in radial magnetic field, the angle between the area vector A and the magnetic field will be 90. So sine 90 value will be maximum, that is 1, and so the torque will be maximum. That is what we want, right? Now the moving coil galvanometer. Let's see its working. Now children, whenever you are placing the moving coil galvanometer in any circuit, so the current will flow through the coil. So as the current will flow, the coil torque will act on it, and the torque is given by the formula NIAB sine theta. But as we have used radial magnetic field, sine theta will become 1, right? So tau equals to NIAB is the torque which is going to rotate the coil. Now, when the coil has been rotated with this torque, there will be a counter torque which will be provided by the spring, which will try to bring the coil to its original position, right? That is the opposing to it. It is known as restoring torque. So that torque is produced in the spring. So let us call it tau S. That is equals to K phi, which is proportional to phi. Phi is the deflection through which the coil has been turned, right? So what happens is, this restoring torque, that is tau S in the spring, it tries to bring the it tries to bring the coil back to its original place. So the torque, the restoring torque in the spring, it goes on increasing, and the tau NIAB, it goes on decreasing. At one position, the tau in the spring, the restoring force in the spring, and the torque in the coil becomes equal. That is, K phi becomes equal to NIAB. Here K is the torsional constant of the spring, or it can be also called as the restoring torque per unit twist. If you make K subject of formula, K will be equal to tau S upon phi. Tau is what? The restoring force, right? Restoring torque per unit twist, right? So here, if you see children, tau equals phi, the deflection phi. If you make phi subject of formula from here, the deflection phi will be equal to, phi equals to NIAB upon K, right? NIAB upon K. So it is NIAB upon K. But if you see children, N, B, A and K all are constant. So you can say that here the deflection in the spring is proportional to the current. Means more the current is flowing, more will be the deflection that will be produced in the galvanometer. Right, children? So this is your formula. Now, children, uh, and there are the two parameters on which with which the galvanometer, how precisely it is going to measure the current, it depends on. First is the current sensitivity. So current sensitivity means for very small current, for very small current, does the galvanometer show deflection? Is the galvanometer sensitive to very small current in the flowing in the circuit? If the galvanometer is showing deflection for very small current flowing in the circuit, then you will say that the galvanometer is very sensitive. So that is your current sensitivity. That is the deflection produced for very small current flowing through it. So it is deflection per unit current. So current sensitivity is denoted by IS. I for current, S for sensitivity equals to deflection. Deflection is phi upon current, that is I. Now we know from this phi upon I, from this equation phi upon I will go that side, will be equal to NBA upon K. NBA upon K, right? So current sensitivity unit will be deflection unit is radian, and I is current, current is ampere or division per ampere. So more is the value of current sensitivity, more precise your galvanometer is. The second parameter is voltage sensitivity. So it is again, children, voltage sensitivity means for very small voltage. Does the galvanometer show the deflection? Is the galvanometer sensitive? So that is deflection produced in the galvanometer for very small voltage? So it is deflection per unit voltage. So deflection is phi, voltage is IR according to Ohm's law. Right? So voltage sensitivity is represented by Vs. V is for voltage, S is for sensitivity, equals to phi upon IR, which is equal to NBA upon K, because phi upon I is equals to NBA upon K. Right? But here you are having R, so here also we will put a R over here. Right? So what will be its unit? Its unit will be phi unit is radian, or you can call it deflection upon, this is what? Voltage. Voltage is V. Right, children? Volt. Right? So this is your voltage sensitivity. So this is your topic, moving coil galvanometer. In the coming topic, we will discuss the last topic of this chapter in the coming video. Okay, children?